Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we're going to look at our third set of notes dealing with gas laws. Now, if you recall our last set of notes, we looked at inverse proportionalities. And the reason we call it inverse proportionality is when we graphed one variable versus the inverse of another, we had a linear relationship. So V over 1 over P equals K, and we use that to establish the relationship that pressure times volume equals a constant. So P1 times V1 would equal P2 times V2. As long as we don't change the temperature of our moles, it stays in inverse proportionality. Now, that's one type of proportionality. The one we didn't look at yesterday was the second type. And that's the direct proportionality, when one variable versus another is already linear. So in the case of volume and temperature, when we graph volume and temperature, we get a linear relationship. So that would mean V over T equals K. Now, this is a direct proportionality. So what we end up with volume and temperature as a direct proportionality is the fact that with Charles' law, which looks at volume and temperature, V1 over T1 equals K, V2 over T2 still equals K as long as we're at constant pressure and amount. So therefore, they're equal to each other. And this is a direct proportionality. Notice mathematically it looks different from Charles' law. P1 V1 equals P2 V2. The reason it looks mathematically different is that was a inverse proportionality. So at constant pressure and amount, the volume of a gas is directly proportional to the Kelvin temperature. Remember, Kelvin temperature is incredibly important. It's the only temperature scale that's truly proportional to the speed of the molecule. At 0 Kelvin, molecular motion would have stopped. So we always have to be in Kelvin when we're dealing with temperatures in this chapter. And that's what we call Charles' law. So volume versus temperature Kelvin gave us our linear relationship, and therefore we can mathematically solve problems involving volume and temperature. So example, a balloon inflated in a room at 24 degrees Celsius has a volume of 4.00 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What's the new volume if the pressure is constant? Once again, this is a sealed balloon, so we're assuming the number of moles of gas in the balloon is constant. And now we're dealing with temperatures and volumes. So first I set up my variable table. The temperature given at the beginning was 24 degrees Celsius, and the volume was 4.0 liters. And the temperature at the end was 58 degrees Celsius. And what we don't know is the volume. But if you recall, and this is a discussion we had yesterday, you first set up your variable table and you need consistent and appropriate units. And while my units are consistent, both degrees Celsius, I've got liters, so I'm going to get a volume in liters. That's not a problem. My problem really is here I don't have appropriate units. Remember I just said Kelvin temperature is appropriate. So before I do anything, I need to add 273.15 and round to find my new temperatures in appropriate units Kelvin. So T1 would be 24 plus 273.15. Now, 24 is uncertain to the ones, so I'm going to round out the 0.15 and I get 297K. Then I do the same thing for 58 degrees Celsius. 58 plus 273.15, since I'm rounding to the ones because my 8 is uncertain in the ones, I get 331 Kelvin. So these are my appropriate temperatures. And now I'm ready to use Charles' law, which is V1 over T1 equals V2 over T2. Now I'm solving for V2. Remember, I need to get the variable on top, and then I need to get it alone. Well, it's already on top, so that's taken care of. But to get it alone, that means I'm going to multiply both sides by T2. Now the T2s on the right would cancel. Since I did the same thing to the left, I maintain the equality. And that means V2 is going to equal T2 V1 over T1. Remember, this is not optional. On the homework, you have to solve it for variables before plugging in the numbers. Now I can pull my numbers from the variable table, and I can set up my math problem. 331 times 4.00 liters divided by 297. That's going to give me that number in the calculator. But once again, I have to round to appropriate units. Everything in this case had 3. So that means I'm rounding to 3 sig figs. 4.46 liters would be my final answer. And remember, if I didn't change my temperatures to Kelvin, I wouldn't get this answer. And therefore, it wouldn't be accurate. Got to be in temperature of Kelvin. Now, the other direct proportionality we're going to look at today is known as Gay-Lussac's law. Gay-Lussac was looking at the relationship between pressure and temperature, and he discovered that at constant volume and amount, the pressure and the temperature in Kelvin were directly proportional to each other. Now, that means pressure graphed versus Kelvin temperature would be linear, and that would mean P1 over T1 equals K. And if P2 over T2 also equals K, then P1 over T1 would equal P2 over T2. It looks just like Charles' law because that was also a direct proportionality. Now, a Gay-Lussac's problem. Gas left in a used aerosol can is at a pressure of 103 kPa at 25 degrees Celsius. If the can is thrown into a fire and the pressure increases to 415 kPa, what's the temperature? Well, first off, One of the things you should understand here is they're directly proportional. So when your temperature is going up by a lot, your pressure is going to go up by a lot, and that's a problem. This is something that you should never, ever, ever do because that aerosol can is basically your grenade waiting to go off. If the pressure increases enough to exceed the ability of the container to withstand it, then that means the container explodes and it's going to spray out shrapnel. So no, don't ever, ever do this. But if it did happen, we could determine what the new temperature was if it got to 415 kPa. So I'm going to use a variable table with pressures and temperatures. My original temperature and my original pressure were 103 kPa and 25 degrees Celsius. My final pressure was 415 kPa. And what I don't know what my final pressure is. So that's my unknown here. Now I've got pressures and temperatures. That's Gay-Lussac's law. But before I can do that, remember, I have to be in appropriate units. So 25 degrees Celsius is a problem. My kPAs, those are consistent. That's not an issue. But I need to change 25 degrees Celsius to Kelvin, and that means add 273.15 and round. And in this case, that's going to give me 298K. Now, that number may end up looking really familiar to you because in many cases, 25 degrees Celsius is considered room temperature. Now, it's a little on the warm side to be room temperature, but it's an easy to remember number. So you often see 25 degrees Celsius, which in math problems would be 298K in a lot of problems. So now we've got appropriate and consistent units. Now we're ready to solve. We've got P1 over T1 equals P2 over T2. Now a lot of times when students first start this, if they haven't been warned about this and practiced it enough, they're going to run into trouble. And that's what I want to show you here. Because in math class, they often shortchanged solving for a variable. So what they particularly say is, well, they isolate the variable, get it alone. So in this particular case, I'm solving for T2. That means I need to get rid of P2. Well, if I divide both sides by P2, then my P2's on the right will cancel, and now T2 is alone. But there's a problem. The first step in isolating a variable, and this is often shortchanged because when you really learn this in middle school, a lot of students just couldn't get it. This was too abstract for them. So you ended up coming up with simple ways to do this, like cross the bridge and other types of things that mathematically give you an answer or give you an equation without really understanding where it comes from. And cross multiplication is an example of that. A lot of times students use this thing called cross multiplication having absolutely no idea why it's mathematically valid, and it leads to problems. And this is one particular case of that. We don't really want to solve for 1 over T2. We don't want to know the inverse of the right answer. We want to know the right answer. So remember when you're solving for a variable that's on the bottom, we first need to get it on top. Now, I want to get rid of that T2, and it's on the bottom. So if I multiply both sides by T2, yes, those two T2s will be gone on the right. But notice where the T2 now is. It's now on top. And now if I want to solve for T2, all I need to do is get it alone. So if I divide both sides by P1, and then I multiply both sides by T1, mathematically I've still maintained the equality, and now everything is going to cancel but T2, and now it is on top. So that means mathematically T2 equals P2 T1 over P1. Be especially careful algebraically on this chapter solving for temperatures because this is going to be the most missed style of question on the test because you didn't get it on top first. So instead of getting the right answer, you're going to get the inverse of the right answer. But at this point, I'm ready to just plug in numbers. And once again, everything's got 3 sig figs, so I need to round my calculator answer to 3 sig figs. But that presents a problem here. This is a tricky one. And I put this in here intentionally to make sure I could remind you of it again. Now, I'm going to round right here. The next digits is 0. So that means I round down to 1200. The problem is if I write 1200, it's got 2 sig figs. If I write 1200 decimal point, it's got 4 sig figs. I need 1200 with 3 sig figs. That means I'm stuck with scientific notation. We looked at this in first semester, but it's been a while. The only way to correctly write this answer to correct significant digits is to put it in scientific notation. So 1.20 times 10 to the third, it's still 1200, but now it's 1200 with 3 sig figs. And my units would be Kelvin. And that ends our set of notes over some of the other gas laws you should know.